Welcome all of you. In the last couple of classes, we extensively discussed about relaxation phenomena. We understood about spin lattice relaxation, spin relaxation, the concepts of what is a relaxation, and what are the sources for such type of relaxation possible in a given system. For example, if spin lattice relaxation, if we have to consider, dominant interaction is the dipolar interaction, and that should be local fields that is generated at the site of the nucleus which is undergoing relaxation should also be at the Larmor frequency. Then only spin can give its energy to the lattice and relax. And we understood the method of determining T1, especially spin lattice relaxation time, using what is called inversion recovery technique, where we apply first 180 pulse. I'll bring the magnetization to minus z axis and then see as a function of time how it grows back, fit it into the exponential curve which is known as mz equal to m naught into 1 minus e to 2 into e to the power of minus t by t1, and we calculated the value of t1. Of course, we understood a lot more concepts and principles, how the energy is given to the lattice, what is all those things. We will not go more into the details. Of course, spin relaxation also we understood, and it is a decoherence which is taking place in the xy plane. That's what we understood. Then we switch it over to NOE. Of course, relaxation phenomena is one of the important things for NOE, where we understood if you saturate a particular spin, and then if the another spin which is close by in space need not be J coupled, in which case we see the change in the intensity of the signal if there is a spatial proximity. By giving energy of this nuclear spin to that, there is a polarization transfer that is taking place. This change in the intensity could be positive or negative. So this we understood what is the reason for that, and we understood the transition probability for single quantum transition, double quantum transition, and zero quantum transition. We came to know that double quantum and zero quantum transition pathways are the things which are responsible for giving rise to change in the intensity. And we know that we have calculated the population difference after irradiating one of the spins in a 2 spins case, and we found out that if the spins undergo preferentially double quantum pathway for relaxation, there is going to be a positive in the intensity enhancement of the signal by 100%. On the other hand, spins undergo relaxation to zero quantum pathway, we observed that there is a reduction in the intensity by 50%. And we understood more about the NOE phenomena, how to measure NOE by a differential, by doing two experiments, a steady state NOE. One, irradiate the particular peak on resonance, and then irradiate off resonance somewhere far away, take the difference and find out the change in the intensity. This change in the intensity can be correlated to the distance between two spins, which goes by 1 over r power of 6. As I told you, the NOE depends upon spatial proximity, and it goes by inverse of r to the power of 6. That is why if there is a small change in the distance, if the distance increases, there is a drastic reduction in the intensity of the signal. NOE signal will come down drastically. And we said that the most probably if the distance between the two spins are less than 5 angstrom, there is a probability that we will see NOE. A lot of things we discussed about NOE, and we said we will discuss transient NOE at a later stage. Okay, with that we will switch over to a different topic today. We are going to introduce little mathematical formulation. It is called product operator formalism. So this is what is normally used to understand the behavior of the spin system in any of the experiment in NMR, be it a simple one pulse experiment, or it could be a multi-pulse experiment, or a multiple quantum experiment, does not matter. And nowadays, as you see, people have designed number of pulse sequences NMR to determine the information that we require in a particular. This experiment is designed in a particular sequence to determine particular type of information can be done. So then how it is designed? To understand the spin dynamics or the behavior of magnetization, or in other words, in simple terms, the evolution of the magnetization under chemical shifts, free precision or J coupling, how it takes place at different stages of the pulse sequence can be understood. For this, a mathematical method is a formalism is there, that is called product operator formalism. We will try to introduce this today. In principle, I wanted to bring this after discussing 2D, because we have discussed 2D in the previous course also a large. This again will come to 2D in this course also. But before that, I thought before we run out of the time, we wanted to discuss product operator formalism. This is a new topic which we are discussing in this course. So I am taking up this. In this, we are applying product operator formalism to understand the behavior of the spins in a simple one pulse experiment or one dimensional experiment. We are not going to 2D, because after introducing 2D for the benefit of the people who did not credit the course or attended the course previous course, I will introduce 2D and then take one or two example of how we apply product operator formalism to understand the pulse sequences. We will come to that later. So right now we will start with the product operator formalism and understand simple one pulse experiments. Okay. So understanding of NMR concept, as I said, right from the first class we have been discussing. There are simple approaches. Simple approach is the classical approach or a semi-classical approach where we discuss based on the vector model. We understood how magnetization is brought from Z axis to X axis and how they start defacing, how they grow back. So all these things we discuss in a classical approach, in a classical vector model. That is one way. But all the time it is not possible to do that. It is not always gives you the complete information, and it is going to be difficult also. The analysis of the complex pulse sequence can also be understood by another theory called density matrix theory. This is an extensive calculation one has to do. It is really, analysis is very complex, and then it takes enormous amount of time and lot of involvement is involved. And another thing is a new approach, and not new approach, a third approach I would say. This approach has already been in the literature for more than 2 to 2.5 decades. So another approach is what is called the product operator formalism. This is a method used to represent the state of the spin system in different pulse sequences. So there are several methods, but by and large nowadays people do not use this type of thing for for a different complicated pulse sequences to understand the spin dynamics, or this semi-classical picture and vector picture is also difficult. So product operator formalism is commonly employed to understand the pulse sequence. Okay. So now we can further going into the product operator. What are these product operators? What is this product operator formalism, or what is the basis of this one? First thing, as I said, there is a density matrix approach. This is also depends upon density operator theory. Product operator is based on density operator theory. One thing is it retains intuitive concepts of the classical or semi-classical vector models. It retains the concept. It is not that it completely get rid of this thing, it is there, but mathematically it is applicable to complex spin system. One interesting thing is it aids in understanding multiple sequences, not only single one pulse experiment or a simple 1D experiment. Multiple experiment, it could be 1D or it could be 2D. Even multiple quantum NMR can be understood by this. Multiple, we have not even introduced what is multiple quantum NMR. I will come to that at a later stage, maybe after introducing 2D. Then we will see how, if there is a possibility, we can see how product operators can be utilized to understand multiple quantum sequences also. One important caution I wanted to give you is, remember, it is applicable to weakly coupled spin half system, and it has also geometrical interpretation similar to vector picture. Easy way to understand this thing. So please, these are the important concepts before we jump into detailed analysis of the product operators. You must remember. Now we will start by going into spin angular momentum, which we discussed in the very first class. Spin angular momentum have given nucleus is given as I. It is a vector and it has three components, Ix, Iy and Iz. All the three components are there. So the three components of the spin angular momentum I is given by Ix, Iy and Iz. That is the first point we discussed already. I am just repeating it. Now if I have to analyze the spin system, in the quantum mechanical analysis we discussed for a coupled spin system of two spins case, both weakly coupled and strongly coupled, we analyzed. As I said, first we have to find out what is the wave function, and then build the Hamiltonian, and then find out the eigenvalues and get the transition frequencies and wave functions and intensities, everything we can discuss, we can find out. So that is what we discussed when we analyze it. Quantum mechanical analysis of the two spin case, when we discuss these things. So the Hamiltonian of system is important, which gives the state of the spin system at different stages of the pulse sequence. We can understand, and this Hamiltonian can be manipulated by depending upon the type of pulses you apply, the type of interactions you bring in between the pulses. All those things are very important. So Hamiltonian can be different. We can manipulate the Hamiltonian. That's one thing. And then, as I said, the Hamiltonian operator tells about the energy of the system, spin system. So its eigenvalues and eigenfunctions, if you know, they are nothing but the energy levels of the spin system. So these are important points which you are already familiar with. We discussed this at stretch in couple of classes about general introduction to NMR and also on quantum mechanical analysis of coupled spin system. Now let us start with a single spin, only one spin. Basic assumption, of course, once I don't have to tell you anything. If I say single spin, it is understood the J coupling is not there. At least to have the interaction, there must be two spins to get the J coupling interaction, or more than two. Since I am considering only single spin case, J coupling is absent, no J coupling. Further, there could be relaxation going on in the different pulse sequences during the pulse and during the delays we apply between the pulses. Spins can undergo relaxation, which we discussed, lot of things we discussed. So that also is there, but what we do is, for our calculation purpose, we ignore that. So point is, since I am considering the single spin, the coupling is ignored or it is not there at all, and relaxation is ignored. This is to make our life simple to understand the product operators. Okay. So with this idea, what we will do is, if I want to understand about the spin system, everything about the spin system can be described by what is called density operator, which is given as rho. Rho is a density operator. If I know density operator, then I can discuss or I can describe all about the spin system of my interest. Okay. So calculation of the rho is very important. If I know rho is 0, I can find out what is rho t as a function of t when at different pulse sequences. If I know rho, I can get the properties of the spin system. So the calculation of rho gives me all the properties of the spin system. Okay. With this, now I know that density operator is needed to understand the spin system. How do we write the density operator for a single spin? We will write down first, for a single spin, what is the density operator. Density operator contains part of Ix, Iy and Iz. As I said initially itself, the spin angular momentum, three components are there. So density operator contains all these terms in different parts. It may not be fully Ix, Iy, Iz, or depends. It can be linear combination of all the three of them. So the linear combination of all the three components of the spin angular momentum is there in the density operator. That is another thing. So I can write mathematically, if I want to understand how the density operator is changing with the time, I can give like this, rho of t, which is equal to Ix plus Iy plus Iz, in each of the term multiplied by a coefficient Ax of t, Ay of t and Az of t. These are the coefficients. So the total density matrix, if I want to find out, calculate at a given time t, for any time t, I can represent as Ax of t into Ix, Ay of t into Iy plus Az of t into Iz. So these are the three terms. So all the three are present in linear combination. One may be present more, one may be less, or two may be present, two may not be present. Only one may be present. So all possible combinations they are there. It depends upon the coefficients Ax, Ay and Az. So amount of each of these is given by the coefficients, and these coefficients can vary with time. Begin a pulse sequence, at some stage you may have Ix, and a different stage of the pulse sequence you may have Iy, or you may have something else. It can happen. So all these coefficients of Ax and Ay vary with time. As a consequence, the rho t is also different. It vary with time. Okay. Now what are these Ax, Ay and Z? When I say it defines part of the Ix is present, Iy is present, Iz is present in rho t, it based on the coefficients Ax, Ay and Az. What are these coefficients? These are just the numbers. Okay, these are just the numbers, nothing else. And these are calculated when you analyze any given pulse sequence. Take a pulse sequence and keep analyzing that, and at eventually you are going to calculate Ax, Ay and Z at some numbers. Okay. So when a pulse sequence is analyzed, we will know the total magnetization. You take any given pulse sequence, let us say I have a 2 pulse sequence with some delay here and here, and see what is the state of the magnetization after 2 pulse. Let us say I apply 90 pulse, and here the spins are in thermal equilibrium. Apply 90 pulse. Here they will evolve, spins will evolve under the influence of chemical shift or coupling if there are more than one spin, and after again I apply 90 pulse along x axis or y axis, and again they will evolve here under precipitation, and see what is going to happen, what is the behavior of the magnetization at the end when you are trying to detect. So that's what we will have to understand. So if I analyze any pulse sequence, then I will know what is the total magnetization in the pulse sequence. So it has certain amount of Ix, Iy and Iz, all are present, and they are related to coefficients Ax, Ay and Az. That is what I mentioned. So all I want to tell you in summary is, take a pulse sequence and analyze it, you will know what is the total magnetization. The total magnetization consists of Ix and Iy and Iz. So the density matrix what you calculate, the density operator at the end is only the components of Ix, Iy and Iz with different coefficients Ax, Ay and Az. Okay. Now with this I say, when I have the components of Ix and Iy and Iz, I can immediately directly correlate to magnetization on x axis, y axis and z axis. Okay. So simply Mx of t is nothing but Ax of t. So Ax coefficient is nothing but the magnetization along x axis. My of t is Ay of t and Mz is Az of t. These are the coefficients that directly related to each other. With this, what are the implications? What does it mean? If I say Mx of t is equal to Ax of t, and My of t is equal to Ay of t, and Mz of t is equal to Az of t, when I say that magnetization directly correlated to the coefficients, what does it imply? What it implies is the amount of Ix magnetization present at any stage of the pulse sequence, if I calculate, it is proportional to Mx. Similarly, the amount of Iy present is proportional to My, and Iz is proportional to Mz. This is a simple correlation, simple relation. When I say that Mx is proportional to Ax, Ay, My is proportional to Ay, Mz is equal to Azt, it means the coefficient when I am telling is correlated to Mx, My, Mz means Ix is proportional to Mx, Iy is proportional to My and Iz is proportional to Mz. This is what it implies from my expression which I gave before. So I know density operator varies with time, that is what I said. In a different pulse sequence, depending upon at what stage of the pulse sequence you are calculating the density operator, it varies with time. So analysis of the sequence, if I want to do, I want to do the calculation of the density operator of a given sequence at any time. Let us say final density operator is after a time t is t rho t. If I want to know what is the final rho t, and I calculated somehow, let us say with all this product operator which you understand now, I found out rho t is final rho t is Ix. What does it mean? That means finally if it is only rho t, the magnetization is along x axis. Rho t, if it is Ix, it is magnetization that is along x axis. If my rho t turns out to be rho of t is Iy, then my conclusion is the magnetization is along y axis. Please understand, the rho of t, when you finally work out, If it turns out to be Ix or Iy, then your conclusion is if rho of t is Ix, the magnetization is along x axis. If rho of t is Iy, magnetization is along y axis. This is the interpretation of this thing. And before we proceed further with product operators, we need to introduce few rotations. Of course, you all know rotations in NMR. Everything in NMR is rotation. Okay, we can understand those things. First, all the pulses are rotations about a corresponding axis you apply. Suppose I am going to apply pulse along x axis, it is a rotation about x axis, then Ix. If I say Ix, I am applying pulse along x axis, there is a then angular momentum operator component is Ix, then it is a rotation about x axis. Similarly, Iy is a rotation about y axis. This is what we know that right from the day one we have been discussing, when all the pulses you apply in different axes can be treated like a rotation. Pulse means you are applying pulse means you are rotating. It is you are rotating this, you are making the spins to undergo rotation. So these are all rotations, pulses are rotations. I will apply a pulse, let us say, and then keep quiet and then start collecting the signal after some time. During this time, between the pulse and the time at which I am acquiring the signal, I am not going to do anything. I will simply keep quiet. It is called free precision. After you apply the magnetization, 90-degree pulse, bring the magnetization to xy plane and then don't do anything. But in this time, till you acquire signal, magnetizations are not, spins are not simply keeping quiet. It is undergoing precision. The precision is along z axis now. You don't do anything. You brought the magnetization to xy plane, but the spins are undergoing precision along z axis. It is a rotation about z axis. So the delays in the between the pulses are called free precision, and that defines the rotation about z axis. Okay. Now what about chemical shifts? If there is chemical shift and spin-spin coupling, they are also rotations. Chemical shift is also a rotation. How the chemical shift evolve in after applying 90 pulse or during the delay. Just let us say I apply a pulse and give a delay. Okay. And then when I apply a pulse and give a delay, does not mean that chemical shifts are not evolving. I apply a pulse and keep quiet. Here chemical shifts can evolve during this delay. J coupling can evolve, and there is a free position, there is a rotation about z axis. See, evolution of the chemical shift here is called a rotation, and evolution of J coupling is also another rotation. So all this can be treated as rotations. Please understand, pulses, delays, chemical shifts and spin-spin coupling, all the four are treated as rotations. Evolution of chemical shift, evolution of J coupling and free precision and application of the RF pulse are all rotations. Now before we understand the rotations in the xy plane, this part we almost discussed this when we were discussing about the pulse space and receiver phase, etc. But just for recapitulation, just remember this thing, the components of the magnetization in the xy plane, we know how to resolve into two components. When the magnetization is brought back to xy plane, they start processing in the xy plane. When it's immediately apply 90 pulse, bring it to x axis, then it start processing in the xy plane. So it develops x and y components. Okay, magnetization develops x and y components. This we know that we have already discussed. And let us say, and this is the x component, this is the y component. X component is cosine of thing Ix into cosine of omega t. What is omega? In the rotating frame it is an offset, or you can call it as a chemical shift, depends upon the chemical, how far it is offset is from the center of the spectral which you have chosen. So that is called offset. When we discussed this when we were discussing about the evolution of chemical shifts and coupling constants. And y component is Iy sin omega t, again omega is a offset or chemical shifts, you can call it. So let us, when I say I bring the magnetization to xy plane, we have x component, y component. The product operator starts processing in the xy plane. I would simply say the product operator starts precessing in the xy plane. It means Ix and Iy start precessing. Okay. With this idea, we will start understanding more about the product operators. First, you put the sample in a magnet and bring the magnetization to xy plane by a 90-degree pulse. That is what I just in the previous slide I said. This is what we will do. Now, this is called free precision. After apply the magnet 90 pulse, bring the magnetization to the xy plane. Now, we have to think of what is called free precision. That means, as I told you, the free precision is the rotation about z axis. Okay, that is what is going to happen now. So, it means x and y components of magnetization keeps on changing with time. When this magnetization is undergoing rotation, the x component, y component also keeps changing with time. What does it mean? The density operator rho is also changing with the time. That is the conclusion. Simply do not do anything, bring in a magnetization from 90 degree from z axis to xy plane by a 90 pulse, then xy components of the magnetization start changing with time. That means density operator is changing with the time. That is the conclusion. So, now we should understand, to understand the rho t, rho of t is the final density operator at the time t. If I want to find out what is rho of t, I must definitely know what is rho of 0. What is rho of 0? Is the density operator at time t equal to 0. So, I should know rho 0, rho of 0 and rho of t. So, I define rho of 0 as the density operator at time t equal to 0, and rho of t is the density operator at the time t. So, these are the two things, rho 0 and rho t we are defining. And if I want to calculate density operator at time t, that is rho of t, magnetization would have evolved with time. So, the beginning I must know what is initial rho 0, that is initial density operator. This is the one which evolves with time under pulses, delays, etc. So, if I know what is rho 0, then I can find out what is rho t by a simple expression like this. This expression is e to the power of minus I h t rho of 0 and then e to the power of I h t. So, this is what is this, the equation which we have to use if I have to calculate rho of t in any given sequence. Okay. Now, you may ask me what is h here. Of course, t is time, of course I and all those things you know. Rho 0 is my initial density operator. What is h? H is Hamiltonian and t is the time at which Hamiltonian is getting changed as a function of time. What is happening to this Hamiltonian, that is what we have to study. So, t is the time, h is the Hamiltonian. Okay. Now, to calculate rho t, I must know what is rho 0. Okay. If then that means I must know the state of the magnetization at the beginning of the sequence. What is the magnetization at the beginning of the sequence? I must know. For example, I have to simply apply a pulse and see the and start collecting the signal. If I want to understand this by density operator, before applying the pulse, let us say I call this as rho 0. What is rho 0 here? It is under thermal equilibrium. Rho 0 is just Iz component here, that is all. So, we must know what is the state of the magnetization at the beginning of the sequence. If I know that, then of course, how that evolves as a function of scale, different pulses and time we can understand. So, if I know rho 0, I can calculate rho of t. This is a very important thing. Okay. As I said, rho t varies with time depending upon the pulses and the delays. It is not same for all the pulse sequences, it is different. It depends upon the pulse you apply, depends upon the delay you give, depends upon sequence of pulses you apply, 1 pulse, 2 pulse, and what type of, whether 90 pulse, x axis, y axis, all those things. So, it depends upon the type of pulses, the phase of the pulses you apply and the delays, all are important. So, the rho t varies with time. So, as I said, when I am considering the free precision, that is just during the delay, I always have to consider the spins undergoing precision along Z axis. I repeated this. I said this some time back. I am repeating it again. The free position, in the free position, there is a rotation around Z axis. Okay. And this is given by Z component. Rotation about Z component, as I said, is Iz. Remember I told you Ix and Iy components. Iy is the rotation about x axis, Iy is the rotation about y axis. Similarly, if I have to consider the rotation about Z axis, it is simply Iz. Iz is the rotation about Z axis. So now with this, we can define operator for different pulses. For example, operator for x pulse is Ix. If I apply a y pulse, the operator for the y pulse, I have to start with Iy. If I want to consider the operator for the z pulse, I have to take Iz. These are the operators for x, y and z pulse. Please note, operator for the x pulse is Ix, operator for the y pulse is Iy, and the operator for the z pulse is Iz. These things I must understand. Then I can generate the Hamiltonians with this idea and then start calculating rho of t. Let us say I want to build a Hamiltonian. That is another thing. I must construct the Hamiltonian. For a free precision, I said rotation is about z axis. So I call this Hamiltonian as a H free, Hamiltonian free, which is rotation, omega is the offset or the chemical shift. It is precision, free precision Hamiltonian is given as H free is equal to omega into Iz. It is the offset. That is the free precision Hamiltonian. You should always remember, when after the pulse, if there is some delay is given, then this is the Hamiltonian you have to apply and find out how the product operators are changing under free precision. When the pulse is applied along x or y axis, let us say I am going to apply the pulse with an RF power omega 1, that is the power of the RF. Then Hamiltonian for the x pulse, if along x axis, I call it as omega 1 into Ix. Omega 1 is the RF power, which is equal to gamma H1 into H1, you know that. Similarly, for the y pulse, it is omega 1 into Iy. These are the Hamiltonians for x and y axis when you apply a pulse along x and y axis. Okay. So after the 90-degree pulse, bring the magnetization to x axis and allow it to undergo free precision. Then you have to use this free precision Hamiltonian and then start calculating what is going to happen. So now the operational sequence, how we do everything, now the time is getting over. So what I am going to do is, I will stop here, we will come back and continue further about the product operators, evaluate about free precision, what happens if under different pulse sequences, everything. So what I wanted to tell you is, today in this class, I started introducing a product operators formalism. It is based on the density operator theory. I told you the product operator contains Ix, Iy and the Iz components of the angular momentum. With it is a linear combination. How much is the rho of t at any given instant of time if you want to calculate the density operator rho of t, which is given as Ax into Ix plus Ay into Iz plus Az into Iz. Of course, Ax of t, Ay, it is time dependent, it varies with time. So Ax and Ay and Az, they are all coefficients. Then finally we understood, it means the mx is nothing but Ax of t, mx of t, my of t is equal to Az my of t, like that. We understood what are the coefficients also. Finally we know the amount of magnetization mx correspond to Ix. Ix can be correlated with the magnetization mx, component of magnetization mx. We understood Ix, Iy, Iz, which is correlated to mx, my and mz also. But also I said, if I have to understand the pulse sequences and what is happening to the density operator at different times of the pulse sequences, I must know what is rho 0. That is the beginning of the Hamiltonian, beginning of the sequence, and where we are applying the pulse, whether the magnetization is along the x axis, y axis or what. If you apply a pulse along x axis I said it is Ix. If I apply the pulse along y axis, it is Iy. And each of them can be treated as a rotation. I said Ix can be treated as a rotation about x axis, Iy can be treated as a rotation about y axis, Iz is a rotation about z axis. All the three we understood. And then while understanding the product operators, how the things evolve, I said everything is rotation. If you apply a pulse, RF pulse, that is a rotation. And then give a delay, don't do anything, that is a pre-precision. And during that time, chemical shifts will evolve, J couplings will evolve, they are all rotations. Everything can be treated as rotations. So then we have to construct a Hamiltonian for pre-precision or different pulse sequences. They are different pulses when you apply. Then you can work out the rho of t. I told you for the Hamiltonian for a free precision is omega into Iz, because in the free precision the precision is rotation is about z axis. Now if I apply a pulse of RF omega 1, RF power omega 1, then Hamiltonian for the pulse, let us say Ix pulse, it is omega 1 into Ix. If I am applying the pulse along y axis with the power of RF omega 1, then Hamiltonian of the pulse along y axis is omega 1 into Iy. So this is what we understood, and now we will continue further. We will come back and see how we can calculate rho t for different sequences with some examples, understand more about product operator, how we can utilize to understand the evolution of the magnetization in different sequences of different time periods of different one or two examples of pulse sequences. So with this I am going to stop now. We will come back again and continue with this. Thank you very much.